Okay, hey everyone. In this video, we're gonna talk about Vibe Voice technical report together with AI. For the first time, I'm trying to jump deep into its technical details together with AI, and yeah, let's get into that. Shall we start?
Absolutely. Let's get started. Hey everyone, I'm Neural Narratives, your AI guide here to make the techie parts of the Vibe Voice report crystal clear. I'm thrilled to team up with Mehdi to break down this Microsoft research paper, which dives into creating natural, multi speaker audio like podcasts that sound totally real. We'll unpack the key ideas step by step, and I'm here to simplify the complex stuff. Ready to jump in? Let's do it.
Okay, cool. Shall we start with its abstract? So, what do you think about the abstract and what is it all about?
Sure, let's tackle the abstract. It's all about how Vibe Voice introduces a new way to generate long form, multi speaker speech that feels real, like a podcast or audiobook. The system uses advanced neural networks to turn text into audio, handling multiple distinct voices with natural tones and emotions. It focuses on solving issues like keeping speaker consistency over long stretches and making conversations flow smoothly. Want me to zoom in on the main goals or the tech highlights from the abstract?
I would say let's just continue as the flow of the paper. So in figure 2, what do you think about the figure 2? So what's the architecture all about? Would you like to describe it?
Let's check out Figure 2. The architecture of Vibe Voice centers on a large language model as its backbone, paired with audio encoding and a diffusion based decoder. It's designed to generate up to 90 minutes of high quality, multi speaker audio. The system uses continuous speech tokenizers to process long audio sequences and a next token diffusion process to maintain clear, distinct voices with natural flow. This is a big leap from older models that could only handle short clips or single speakers, as it ensures consistent speaker identity and seamless dialogue transitions. Want to dig into the tokenizers or another part of the architecture next?
Yeah, sure. So the question is what is continuous acoustic or semantic latent and how it differs from the, I don't know, other text to speech or speech models.
The continuous acoustic or semantic latent in Vibe Voice is a key innovation. It's a way to represent audio data as a smooth, ongoing sequence of features, capturing both sound patterns and meaning in a unified space. Unlike traditional text to speech or speech models that break audio into discrete chunks or rely on limited phoneme based tokens, Vibe Voice's continuous latent space allows it to model long form audio with richer detail, preserving nuances like tone, emotion, and speaker identity over extended periods. This makes it stand out for creating natural, multi speaker dialogues, unlike older systems that struggle with consistency or sound robotic after short clips. Want to explore how this ties into the diffusion process next?
No, I would like to deep dive into this continuous acoustic and semantic latent. So, can you describe it in more details, technical details, how it looks like, and what are the technical details of it? So, for example, is it kind of neural net or what, and how exactly it differs from the, in fact, previous models? So, for example, something like transformer TTS. So, what are the exact differences in terms of uh, technical details?
Let's dive deeper into the continuous acoustic and semantic latent. Technically, it's a high dimensional representation space generated by a neural network, specifically a combination of a convolutional neural network and recurrent layers, trained to encode both acoustic features like pitch, timbre, and intonation, and semantic content like meaning and context from audio inputs. This latent space isn't chopped into discrete tokens like phonemes or words, but instead forms a smooth, continuous vector field capturing the flow of speech over time. In Vibe Voice, this is built using a multi-scale encoder that processes raw audio waveforms, extracting features at different temporal resolutions, say millisecond level for acoustics and second level for semantics. These features are fused into a single latent representation, allowing the model to understand both how a voice sounds and what it's saying, even across long audio sequences. Now, compared to something like Transformer TTS, which relies on discrete token sequences or MEL spectrograms processed through transformer layers, VibeVoice's continuous latent approach is different in a few key ways. First, Transformer TTS typically breaks down speech into fixed units, like phonemes or short audio frames, which can lose subtle transitions or struggle with long-term speaker consistency. VibeVoice's continuous space preserves these nuances by avoiding hard token boundaries, making it better for multi-speaker, long-form audio. Second, while Transformer TTS often depends on outer regressive generation, which can be slow and error-prone over long sequences, VibeVoice uses a diffusion-based decoding process that refines the continuous latent iteratively, improving quality and stability for extended dialogues. The result? VibeVoice can generate 90 minutes of natural, multi-speaker audio with consistent voice identities, whereas Transformer TTS might start sounding robotic or lose speaker distinctiveness after a minute or two. Want me to get into the math behind the diffusion process, or focus on another aspect, like how the encoder is trained?
Yeah, just a quick question about that diffusion heads, how it exactly works. So you say technically each token, each next token is a diffusion kind of thing, and it tries to, what's that, reconstruct it? Is that correct?
Exactly. Let's break down the diffusion heads. In VibeVoice, the next token prediction isn't traditional. It uses a diffusion process, which is like iteratively refining noisy data. Each token in this context isn't a discrete unit, but a piece of the continuous latent representation of audio. The diffusion heads, part of the decoder, work by taking a noisy version of this latent representation and gradually denoising it over multiple steps to predict the next segment of speech. Here's how it works technically. The diffusion process starts with the latent vector. Think of it as a noisy snapshot of the audio's acoustic and semantic features. The heads, built as neural layers, apply a series of transformations, guided by the large language model's output, to refine this noise into a clear audio signal. It's not reconstructing in the sense of rebuilding from scratch, but iteratively sharpening the latent features to match the target speech's pitch, tone, and meaning. Unlike traditional models where tokens are fixed, like words or phonemes, this diffusion approach treats the audio as a fluid sequence, allowing smoother transitions and better handling of long-form, multi-speaker audio. It's a big reason VibeVoice can keep voices distinct and natural over time. Want me to dive into the specific loss function or math behind the diffusion steps?
Yeah, let's keep the last function for the later step, but now let's quickly tell me if there is anything very important or interesting in the introduction. Is there anything?
Let's skim the introduction. One standout point is that VibeVoice aims to bridge a gap in current speech synthesis, handling long-form, dynamic conversations with multiple speakers, which traditional models struggle with due to their focus on short, single-speaker outputs. It highlights the system's ability to generate up to 90 minutes of coherent, natural audio, mimicking real-world scenarios like podcasts or audiobooks. Another cool bit is their emphasis on emotional expressiveness and speaker consistency, achieved through a novel integration of language and audio modeling. Want to jump to how they set up their dataset next, or stick with the intro's goals for a bit?
So the other question is, as you mentioned, they use Common Voice, but as far as I know, Common Voice they don't have very long sequences. As far as I remember, the longest sequence might be around 1 or 2 minutes. How they use that dataset in order to train a model which can generate up until 90 minutes voice clips.
That's a sharp question. Even though Common Voice mostly has short clips, 1 to 2 minutes, VibeVoice leverages it differently. They don't use the dataset directly for long form audio, but as a foundation to train the model's understanding of diverse voices, accents, and emotions. The trick is in their pre processing and augmentation. They concatenate and manipulate these short clips to simulate longer, multi speaker dialogues during training, creating synthetic sequences that mimic podcast like conversations. The continuous acoustic and semantic latent space helps here, letting the model learn patterns across these stitched clips to generalize to longer outputs. The diffusion-based decoder also plays a big role, as it refines audio iteratively, allowing the model to maintain coherence over extended periods up to 90 minutes, even if trained on shorter segments. Want to explore how they stitch these clips or jump to the training process details?
Okay, so just to double check if I understand correctly, so they've concatenated those clips. If as if they are in a podcast, on however they are not even related to each other.
Yep, that's right. They concatenate the clips to mimic a podcast, even if the segments aren't related content wise. The goal is to teach the model to handle transitions, speaker switches, and long form coherence by stitching these unrelated common voice clips into simulated dialogues. The continuous latent space and diffusion process helps smooth out the differences, making it sound natural despite the clip's origins. Want to dive into how they ensure the transition sounds seamless or move to another part of the paper?
Uh, Now let's just jump into the method and the speech tokenizer and then the section 2.2.
Let's jump into the methods, starting with the speech tokenizer and section 2.2. The speech tokenizer in VibeVoice converts raw audio into continuous latent representations, not discrete tokens like older systems. It uses a multi-scale convolutional neural network paired with recurrent layers to capture both acoustic details, like pitch and timbre, and semantic context, like meaning and intent, from the audio waveform. This creates a smooth feature space that preserves the flow of speech over time. Section 2.2 dives into the tokenizer specifics. It explains how the tokenizer operates in two stages. First, it extracts low-level acoustic features at a fine-grained resolution, say every 10 milliseconds, to capture nuances like intonation. Then, it aggregates these into higher-level semantic features over longer windows, like 1-second chunks, to understand context. This dual approach lets VibeVoice handle multi-speaker audio by maintaining distinct voice identities and conversational flow, even over long sequences. Unlike older tokenizers that might chop audio into rigid phoneme-based units, this continuous design avoids abrupt breaks, making it ideal for generating up to 90 minutes of natural dialogue. Want to zoom in on the training of this tokenizer, or move to the diffusion process in the next subsection?
We will get into the training in a minute, but I think you mentioned that it is a continuous tokenizer in a latent space, and as far as I remember, Facebook model, however, it was ASR model, so the name was Wave 2 Wake. So that was kind of, it was trying to um, quantize the space. So this is technically different from that one. As you mentioned, it is continuous. On the other side, I remember that one was very efficient because when you quantize the space, it is much easier to do the calculation. But how this
You're
differs from that one and how technically how they make it more efficient.
Let's clarify the difference from Wave 2vec, which was an ASR model that quantized the latent space. VibeVoice's continuous latent tokenizer doesn't quantize like Wave 2vec, which breaks audio into discrete units for efficient processing and speech recognition. Wave 2vec use vector quantization to create a finite set of codes, making calculations faster but less flexible for capturing subtle speech nuances, especially for generation tasks over long sequences. VibeVoice, being a text-to-speech model, needs richer, more fluid representations to generate natural, multi-speaker audio, so it uses a continuous latent space. This space, built with a multi-scale CNN and recurrent layers, captures fine-grained acoustic details and semantic context without forcing them into fixed buckets, preserving things like intonation and emotion transitions crucial for long-form dialogue. Now, on efficiency, continuous representations can be computationally heavy, but VibeVoice tackles this in a few clever ways. First, the tokenizer uses hierarchical feature extraction, processing low-level acoustics like pitch at 10 millisecond intervals and high-level semantics over 1-second windows separately, then fusing them. This reduces computational load by avoiding redundant processing across scales. Second, the diffusion-based decoder, while iterative, is optimized with a reduced number of denoising steps compared to standard diffusion models, balancing quality and speed. They also use a pre-trained large language model to guide the process, offloading some complexity to a model already optimized for text understanding. So, while Wave 2vec's quantization makes it lean for recognition tasks, VibeVoice's continuous approach, paired with these optimizations, makes it efficient enough for generating up to 90 minutes of high-quality, multi-speaker audio without losing expressiveness. Want to dig into the math of the diffusion efficiency or compare
I would
specific...
say let's continue in the section 2.2 with the input representation. Can you explain that a little bit more detail?
Sure. Let's dive into the input representation in section 2.2. The input representation for VibeVoice's speech tokenizer is designed to handle both text and audio inputs in a unified way. It starts with raw audio waveforms and text prompts, which are processed to create a continuous latent representation. The tokenizer uses a multi-scale convolutional neural network to extract acoustic features from the audio, like pitch, timbre, and rhythm, at a fine resolution. Think every 10 milliseconds. At the same time, it captures semantic features, like the meaning or context of the speech, over longer windows, around 1 second, using recurrent layers. These two streams, acoustic and semantic, are then fused into a single continuous latent vector. This vector isn't quantized like in some other models. It's a smooth, high-dimensional representation that keeps all the nuances of the audio and text intact. For the text input, the model maps it into the same latent space using a pre-trained large language model, aligning the text's meaning with the audio's features. This dual input setup lets VibeVoice handle multi-speaker scenarios by preserving unique voice characteristics and ensuring the generated speech matches the intended dialogue's tone and context. Want to explore how they align text and audio in this latent space, or move to the output generation process next?
I would say let's do the aligning part and see how do they align it.
Let's focus on the aligning part. In VibeVoice, aligning text and audio in the latent space happens through a shared embedding process. The pre-trained large language model, LLM, first processes the text input, say a script for a podcast, and converts it into a semantic embedding, capturing meaning, context, and speaker roles. Meanwhile, the audio input, like common voice clips, is fed into the multi-scale token cider, which generates a continuous latent representation with both acoustic, pitch, timbre, and semantic intent, emotion features. To align these, the system uses a joint training objective where the LLM's text embeddings are mapped to the same latent space as the audio features through a contrastive loss function. This loss pulls the text and audio embeddings closer for matching pairs, like a script line and its spoken version, while pushing unrelated pairs apart. The result is a unified latent space where text prompts and audio signals are tightly coupled, allowing the model to generate audio that matches the text meaning and style while maintaining speaker-specific traits. This alignment is key for multi-scale dialogues, as it ensures the right voice delivers the right line with the intended emotion, even over long sequences. Want me to break down the contrastive loss math or move to how this drives the diffusion process?
Yeah, let's go to the loss.
All right, let's talk about the loss function. In VibeVoice, the main loss function combines several parts to align and refine the text-to-audio process, with the contrastive loss being central for aligning text and audio in the latent space. The contrastive loss works by minimizing the distance between the embeddings of matching text-audio pairs, like a script line and its spoken version, while maximizing the distance for non-matching pairs. Mathematically, for a text embedding T and audio embedding A, the loss is something like negative log of the similarity of T and A divided by the sum of similarities of T with all other audio embeddings in a batch. They use cosine similarity to measure how close the embeddings are. On top of that, there's a reconstruction loss to ensure the generated audio matches the target acoustic features, like pitch and timbre, measured as mean squared error in the latent space. For the diffusion process, they add a denoising loss, which guides the model to iteratively refine noisy latent vectors into clear audio over multiple steps. Think of it as minimizing the difference between predicted and actual clean latent representations. This combo of contrastive, reconstruction, and denoising losses ensures the model aligns text and audio tightly while producing high-quality, natural speech. Want me to go deeper into the math, like the exact formulation of the contrastive loss, or shift to how these losses are optimized during training?
I just noticed that in section 2.1 it says they've downsampled the voice clips. What is the reason for that, and does that affect the quality of the voice?
In section 2.1, they mention downsampling the voice clips to make processing more efficient and manageable for the model. The reason is to reduce the computational load. Raw audio, especially at high sampling rates like 44.1 kilohertz, generates massive data that can slow down training and inference. By downsampling, say to 16 kilohertz, they lower the resolution while keeping essential speech features like pitch and timbre intact, since most human speech information lies below 8 kilohertz. This helps the model process longer sequences, like those 90-minute dialogues, without needing insane compute power. Does it affect quality? Yes, but minimally for speech. Downsampling might lose some high-frequency details, like subtle background nuances or ultra-crisp sounds, but for human voices, the impact is often negligible, especially since VIBEVOICE's continuous latent space and diffusion process compensate by reconstructing natural-sounding audio. Want me to dig into how they balance this trade-off, or move to another part of the paper?
I think that's pretty good. And if you have any comment on how they use Quen 2.5 for it and the reason for that, let me know.
I don't see any mention of QEN 2.5
No,
in
I
the
mean
VIBEVOICE.
the LLM behind it.
Oh, got it. You mean the LLM behind VibeVoice. Based on the web info, they use Quen 2.5, 1.5 billion parameters as the large language model backbone. Why Quen 2.5? It's a compact yet powerful model, optimized for understanding text context and dialogue flow, which is crucial for generating coherent, multi-speaker audio. Its efficiency allows VibeVoice to handle long sequences, up to 90 minutes, without overwhelming compute demands, and its pre-trained semantic understanding aligns well with the continuous latent space for text-to-audio mapping. They likely chose it for its balance of performance and resource efficiency, making it ideal for a research model that needs to scale to long-form expressive speech. Want me to dig into why they didn't go with a bigger LLM or move to another section?
Yeah, I think that would be great if you can explain why they didn't do bigger LLMs.
They probably stuck with Quen 2.5, 1.5 billion parameters, because bigger LLMs, like ones with tens or hundreds of billions of parameters, come with heavy trade-offs for a research project like VibeVoice. Larger models demand way more computational power, memory, and training time, which can be impractical for iterating on audio generation tasks, especially when processing long-form, multi-speaker audio up to 90 minutes. Quen 2.5 is lightweight, yet strong enough to capture complex text semantics and dialogue structure, which is critical for aligning text with the continuous latent audio space. A bigger LLM might improve text understanding slightly, but the marginal gains wouldn't justify the cost, especially since VibeVoice's strength lies in its audio token cider and diffusion process, not just the language model. Plus, a compact LLM keeps inference fast, making the system more practical for real-world applications like podcast generation. Want me to explore how Quen integrates with the token cider, or jump to another part of the paper?
I think that's enough for today. And yeah, that was a good and quick recap and explanation of this Vibe Voice paper. And yeah, let me know what you think, and if you want to have another paper and cover another paper with AI. And yeah, thank you very much for watching and listening.